Okay, guys, welcome. In this video, we're going to talk about the binomial theorem. Okay, so for the motivation for this, first we're just going to compute n choose k for a couple different things here. Okay, so for n equals 2, if I have n choose 0, n choose 1, and n choose 2, we want to see what these are. Well, if we follow our formula, this is n factorial over 0 factorial times n minus 0, which is just n factorial. Now, 0 factorial is 1, so we can think of that as not even being there, and n factorial over n factorial will give us 1. Now, n choose 1, again, n is 2 here, so it's 2 factorial over 1 factorial times 2 minus 1, or 1 factorial. So since 1 factorial is just 1, we're going to get 2 over 1, so this is 2. And then for 2 choose 2, these should really all just be 2's. Right, this is going to be 2 factorial over 2 factorial times 0 factorial. So this will again give us 1. Okay, now for 3, we're going to have 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. Now we'll only compute the first 2 of these because that's all we're going to need, right? And I'll show you what I mean, because 3 choose 0 would be 3 factorial over 0 factorial, 3 factorial, and that's just 1. But remember from before that n choose k is the same as n choose n minus k. So in this case, this is going to be the same as 3 choose 3. So this will also be 1. Now 3 choose 1 is going to be 3 factorial over 1 factorial, 2 factorial. And if we do this, we're going to be left with a 3. So then same thing for this one. Okay, and then finally, if we do this for 4, we want 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. Well, 4 choose 0 is 4 factorial, 0 factorial over 4 factorial, so that's 1. So is 4 choose 4. Okay, now 4 choose 1 will be 4 factorial over 1 factorial, and then 4 minus 1 is 3 factorial. So here we're going to get 4. So then here we also get 4. Now 4 choose 2, we're going to get 4 factorial over 2 factorial, 2 factorial. So we're going to get a 4 times 3 times 2 times 1, but I won't write it. And then here we're going to get 2 times 2. So 2's cancel, and then I'll get 12 over 2, which is a 6. All right, so that's sort of these first couple. All right, now we're going to find the decimal, or not the decimal expansions, the factored expansions for these. So x plus y squared is x plus y times x plus y. And if you FOIL these, you'll find this is x squared plus xy plus xy plus y squared, which is x squared plus 2xy plus y squared. If we do this for x plus y to the third, we can say this is x plus y squared times x plus y. We just found that x plus y squared was x squared plus 2xy plus y squared. So if we multiply this out, we're going to get x to the third plus 2x squared y plus xy squared. And then we're going to get plus x squared y, and then plus a 2xy squared, and then plus a y to the third. And if we add these together, we're going to get x to the third plus 3x squared y plus 3xy squared plus y to the third. All right, and then for the fourth one, this we could think of as x plus y to the third times 1 more x plus y. So this is x to the third plus 3x squared y plus 3xy squared plus y to the third times x plus y. So if we multiply this out, we're going to get x to the fourth plus 3x to the third y plus 3x squared y squared plus xy to the third. And now if we multiply through by y, we're going to get a plus 3, sorry, not plus 3. We're going to get a plus x to the third y. We're going to get a plus 3x squared y squared. And then a plus 3xy to the third, and then plus y to the fourth. So it looks like when we combine our like terms, we're going to get x to the fourth plus 4x to the third y plus 6x squared y squared plus 4x y to the third plus y to the fourth. Now let's look at the similarities between all this junk that we just computed, right? For the binomial coefficients, when n was 2, we got 1, 2, 1. And of course, those are the coefficients for the expansion of x plus y squared. When n was 3, we got 1, 3, 3, 1. And those are these coefficients. And then when we did n equal 4, we got 1, 4, 6, 4, 1. And of course, those are those coefficients. So now we're going to illustrate sort of the general pattern for n equals 5, right? So of course, we want to expand out x plus y to the fifth. So we want to eliminate parentheses by multiplying each term in one set of parentheses by one term in another set of parentheses, and so on. So let's say that I pick this x, and then I pick the other 3 to be y. Right? Now that's going to give you an x squared y to the third, right? Now, of course, how many ways could you have done this to get x squared y to the third? Well, of all the ways to pick 3 y's, which would leave the other 2 being x's, you're basically choosing 3 from 5, which can be done in, of course, 5 choose 3 ways, right? So we get that each of these coefficients are just the binomial coefficients. So essentially, we can form a theorem that says that the coefficient of x to the n minus k, y to the k in the expansion of x plus y to the n is n choose k, right? So x plus y to the n is given by this formula here, right? We just increase for our binomial coefficients. All right, so let's do this proof by induction. So for the base case, we could say that n is equal to 0, right? So then we want to show that x plus y to the 0 is equal to 0 choose 0 of x, y, both to the 0, I guess, kind of silly. All right, but everything is to the 0 power, so we're going to get 1 is equal to 1, so of course that works. Now for the inductive case, we'll assume that this is true for n minus 1, right? In other words, the coefficient of, now let's see, so in the original it was x to the n minus k, so I want x to the n minus k minus 1, y to the k, is, or we say in the expansion of x plus y to the n minus 1 is n minus 1 choose k. And we want to show that this is true for now n. Give myself a little bit more room. Any minute now. Here we okay. All right, cool. Okay, so here's what we want to show. We want to show that x plus y to the n is equal to now n choose 0 times x to the n plus n choose 1, x to the n minus 1 plus blah, 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 n minus 1, sorry, n choose n minus 1, x to the, let's see, and I need a y here, and then x to the 1, y to the n minus 1, plus n choose n of y to the n. All right, well, let's separate this. We know that we're going to have an x plus y to the n minus 1, so we can use our inductive hypothesis times an x plus y. Now we know, based on our inductive assumption, we know that this part, and I'll write this part in purple, is going to be n minus 1 choose 0, x to the n minus 1, plus n minus 1 choose 1, x to the n minus 2, y, plus n minus 1 choose n minus 2, x to the first, y to the n minus 2, plus n minus 1 choose n minus 1 of y to the n minus 1. And I want to multiply this all by x plus y. Okay. So now what we have to do is we have to distribute all of this junk. All right, so let's do that. So if I distribute the x times everything, here's what's going to happen. I'm going to get n minus 1 choose 0 times x to the n plus n minus 1 choose 1, x to the n minus 1 times y, plus dot, 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 plus n minus 1 choose n minus 2, x squared y to the n minus 2, and then plus an n minus 1 choose n minus 1 of x y to the n minus 1. Okay, now let's multiply through by y. If we multiply through by y, then we're going to have an n minus 1 choose 0, x to the n minus 1 y, basically everything's going to be shifted over, plus n minus 1 choose 1, x to the n minus 2 y squared, plus dot, 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 plus n minus 1 choose n minus 2, x y to the n minus 1, and then plus n minus 1 choose n minus 1 of y to the n. Okay, now we just have to combine like terms. Now I only have one x to the n and one y to the n term, and both of their binomial coefficients are going to be equal to 1, so I'm going to change this to an n choose 0, x to the n, right, because these two are equal, and this is going to be an n choose n of y to the n. I'm allowed to do that because n choose n and n minus 1 choose n minus 1 are the same thing, just as n minus 1 choose 0 and n choose 0 are the same thing. Okay. Well, now here, let's look at these two terms. What's n minus 1 choose 1? Well, it's n minus 1. X to the n minus 1, y. And then I'm going to get plus n minus 1 choose 0, which is just 1, x to the n minus 1 times y. But of course, both of these are going to give me an n times x to the n minus 1 times y, which is n choose 1 of x to the n minus 1 times y. All right? And of course, you can show this for all the terms, but we'll just show this with maybe one more, right? If I were to combine, let's see, if I were to combine these two terms, it would give me a plus xy to the n minus 1 plus an n minus 1 xy to the n minus 1 And just as they did in the other example, they're going to give me an n, choose n minus 1, x, y to the n minus 1. Right? And it works out that all the stuff in the middle will give you a similar result. So we get what we want. We get the n, choose 0, n choose 1, and then all the way increasing up the binomial coefficients until we get to the end. All right, and if you really want to, you can work out the messy details of the inside, but that's generally the idea. Okay, so that concludes this video on the binomial theorem. I hope you enjoyed, and I'll see you next time.